Bismillahirrahmanirrahim. This is another video from chapter number 7, step response of an RL circuit, and this is a very interesting question. And for this I have received a request from a student. So let's see the circuit. If the input pulse, this is the input pulse, is applied to the circuit and figure, determine the response of IT. So this current IT through the inductor we have to find. Now the first thing we have to keep in mind that this is the formula that we have learned in the book. So actually we are going to solve this formula. And as we have discussed in several of my videos, there are three parameters that we need to find. One is I0, the other is I infinity, and third is tau, this tau here. Now first of all we have to define this input pulse. How can we write it? Okay, we have to write it in terms of unit step function ut. Now if we start a function ut like here with the magnitude 10, this will become 10 ut. But this is continued till infinity. We have to end it at 1. That means we have to subtract a similar circuit at this point as shown here. So same magnitude, opposite, that is subtracting. And now when you add this, the net output will be 0, which is here 0. After 1, the output is 0. So in terms of ut, we can write this function or this as 10 ut minus ut minus 1. This is as shifted. T minus 1 is shifted function at t is equal to 1. Okay, so we were here. Now what we'll do is we'll separate these two parts. I'm calling this as part 1 from 0 to 1, from t0 to 1, this I'm calling part 1, and from 1 onward, this one we'll call it as part 2, which is for t greater than 1. Okay, now I just recall what I have in several of my videos. I have tried to explain this. This is for a capacitor charging circuit, or this is the step signal applied for a capacitor, and in that case the capacitor will charge gradually up to this point. Now before this point it was steady state because no signal was applied, so this part is called the steady state part for t less than 0. And then the moment this signal was applied, the capacitor will start charging, and this will charge up to what is called 5 tau time. So this portion is the transient portion, and then it becomes a steady state. So we call this as t greater than 0, or we also call it as t infinity. So these are the three things that we have to keep in mind. And one more point is the concept of 0 minus 0 plus. Now if this is the origin as 0, just slightly before it will be called t0 minus, and just slightly after it will be called t0 plus. And this has a significance that the capacitor voltage does not change. Whatever is the voltage here, same voltage will remain here. And in case of an inductor, the inductor current does not change. Whatever was the current here, same will be at this point. Okay, now in our case, when we are talking of the first part, which is, it is like an impulse signal, so we will follow this time values given here, and we'll follow this graph as well. And what will happen in the second case, we'll see in the next slide. Okay, so in the second case, part 2, there will be some changes. The first is the change in the origin. This will now start from 1 instead of 0. And so same, we're just keeping 1 here. This will now be from 0 t less than 1. This will be for t greater than 1, and this will be t greater than 1. And the 0 point will now be 1, and it will be t1 minus and t1 plus. Also, the start point we will call t minus 1 is equal to 0. This is how much it has shifted. T minus 1 is equal to 0. If you calculate from here, then t will be 1, which is here. Okay, so with this knowledge, now we solve part A. So this is the input. Now before 0, there is no signal. Okay, this is what we have to find out. So the first thing, for t less than 0, I0 minus or I0 plus or I0 is equal to 0 because there is no signal in this region. And since there is no signal before t is equal to 0, therefore the current will be 0. Now we come to t greater than 0. Now, although this is small, but all three parameters will be dealt here. This was the 0 point, this we will say is the transient area, and after that it will become the steady state area. So for t greater than 0, we will calculate the infinity. Now in this area, when it is t greater than 0 or infinity, the circuit is again in steady state condition. And in steady state condition, the inductor will behave like a short circuit. The input voltage is 10 volt. Now what will be the current? You can see current from here going here will not pass through this because this has 20 ohm resistor, whereas this path has 0 resistance. So the current will pass through this, and therefore the current value will be 10 volt divided by 5 ohm. So we'll say that I infinity is 10 volt divided by 5. That means 2 amperes. Okay, so I0 we have found, I infinity we have found. Now we need to find tau. And tau is for the inductive circuit, it is given by this formula, L divided by R Thevenin. R Thevenin we can find from this circuit by shorting the voltage source. So once we short the voltage source, we can see this 5 ohm and 20 ohm resistance are in parallel. If we look from here, we are looking from here. So R Thevenin is 5 parallel 20, which is equal to 4. Now plugging in, the L is 2. So 2 over 4 is 1 over 2. So tau is 1 over 2. So we have found all the three unknowns. Now we'll plug in the values in this equation for current. I infinity is 2, I0 was 0, this is 2, tau is 1 over 2, and solving this, this is our final answer. So this is the current in the first part. Now let's move to the second part. Now this was the second part, and virtually you can see this 10 positive, 10 negative means net is 0 volt. So this 0 volt here. And keep this diagram in mind. First of all, we have to calculate I0, or in this case I1, I1 negative. And we don't know the conditions actually, but we know what was the current before here. So we'll use that current. This was the equation for the current before this point, before 1. And if we put here t is equal to 1. Okay, now this is the, this was the, again, the current equation that we have to find. Modifying this, I'm just writing I knew. So we know the previous I infinity and this I infinity new. I0 will now become I1 because we are starting from point 1, and then tau will be this from here, t minus 1. Instead of e raised to the power minus t, it will be e raised to the power minus t minus 1 divided by tau. So this equation will solve. Now how much is I1? So I1, the easiest way is that we have found IT for before this period, and if you put in this equation t is equal to 1, we get I0 minus, which is equal to I0. So IT, this value, we put t is equal to 1. So putting t is equal to 1, we get this value, and solving it is 1.729. So this is our initial current, initial condition. Now let's come to the final or the infinite. Now from the circuit, I infinity is 0. How? Because this voltage is 0. Since this voltage is 0, so no matter how long you keep it on, there will be no current flowing, and therefore this is 0. And now for tau, we again short circuit this source, which is already 0, and find the R Thevenin as we did previously. So it is 4. Putting in the value, tau is 1/2. So we have found here also 3 parameters. I1 we have found, I infinity we had found, and tau we have found. And this was the initial current for t less than 1. So we'll use these values in this equation. I infinity is 0, I1 1.729, this is 0, e raised to the power minus t1 over tau. Tau is half. So it will be now this value 1.729 e raised to the power minus 2 t minus 1. This is IT for the second part. So the total value, we can write it that this was the current for the first part from 0 to 1, this current, and this current is from here for the time t greater than 1. So I hope you have been able to follow this. Please let me know through your comments. Thank you. Don't forget to subscribe and share between your friends.